Okay, I'm ready.
Hey everyone, welcome to the MacMillan Space Center. Michael here, along with our astronomer, Rachel. All this week, we have been excited about OSIRIS-REx and its final tag event with Asteroid Bennu.
Yeah, and it's kind of funny to think that the whole thing, the whole tag event, like the actual sample was only like 5 to 6 seconds long, but there's so much preparation leading up to it.
I know, and it was really interesting. So what we're going to do is we're going to watch a video of kind of like of the event. It was really quick, and it's amazing just how much preparation has gone into these few seconds, like years of development. The launch a few years ago, the approach of the asteroid, mapping the asteroid, getting all of this to ready. And what we're going to see is not only a video and pictures of the event, but we're also going to see the team at NASA, at Goddard. You're going to see sort of like the stress sort of like fall off their faces because, yeah, this was a pretty significant event for them. So what we'll do is also I put into the description of this video some of those links that you can rewatch them afterwards. You can also go and learn a lot more, and then we'll of course take any of your questions that you have about OSIRIS-REx, about Asteroid Bennu, because yeah, like we said, we were pretty excited. So let's watch a quick little video here to get us primed up for what we're going to talk about. So cool. What I love about this video, I'd love to interpret a little bit. So we did see a few different things in there. We did see some actual photos. Now they are stitched together to make it look like a video, but that's just to distinguish between like the photographs and the video. It does sort of look like video. There was also some animations in there as well, but for the most part, a lot of what we did see was actual video, right, Rachel?
Exactly, yeah. So just at the beginning, the smoother video is an animation, and then the kind of more choppy one would be the photos stitched together.
Yeah, and then of course there was that animation that showed sort of like from afar, what it would look like as OSIRIS-REx came down close to the asteroid. And that view that we saw, we had seen that view before during their test, almost like a month ago, right? Sort of like that arm getting like really, really close to the surface. And I remember looking yesterday at some of those videos. I was like, oh, I've seen this before. And then all of a sudden, it actually went into motion, and it was very quick. So it goes down. It's like the whole event took like 5 seconds. Is that right, Rachel?
Yeah.
And so maybe like walk us through a little bit like what happened in that 5 seconds.
Sure. So the arm extended, the tag arm, and it made contact for 5 to 6 seconds, but most of the collection happened in the first 3 seconds. So really, the entire event was 3 seconds long. And what it did is it shot a little burst of nitrogen gas to disturb the surface, and it kind of stirred up and mixed up some of the material so that it could be collected by the arm, and then the arm retracted, and on its way it goes.
There we go. Okay, so if anyone has any questions about any of that, but Rachel's going to go a little bit more in depth. Of course, you can put it into the chat. You can also leave a comment later on as well. Rachel and I will be happy to answer your questions even after we're done going live here. But take it away, Rachel. Let's dive into some of this stuff that OSIRIS-REx has found out about Bennu.
Cool, thank you. So I thought I would start off with what the acronym stands for, OSIRIS-REx. So the O stands for origins, and that really means a lot of things. It talks about the origins of the materials in the asteroid, but also our origins as well, because this asteroid serves as sort of a time capsule for the formation of our solar system. And the next is the SI, that's spectral interpretation. And basically what that is for is we're going to compare the data that we get in situ or on site on the asteroid to data that we have here on Earth from Earth-based observatories and space-based observatories. And then the RI is resource identification. So we're looking at the geological history of this asteroid. S for security, and we're looking for this thing called the Yarkovsky effect, which I'll talk about later. But it's basically this non-gravitational force that does alter the trajectory of the asteroid. And finally, we have REx, the regolith explorer, and that's looking at sampling the surface material or regolith of the asteroid. So asteroid operations for this mission began in 2018 when the spacecraft captured its first image of Bennu from a distance of around 2 million kilometers. Now, the spacecraft's official arrival at Bennu occurred a year or later that year when OSIRIS-REx transitioned from flying toward Bennu to orbiting and operating around it. Now, while at the asteroid, OSIRIS-REx surveyed and mapped Bennu, navigating in close proximity to the asteroid, and ultimately led up to the spacecraft breaking orbit, which you can see here, and then sampling the surface. And you can see the trajectory here where it goes onto the surface, touches and goes very quick. So from the initial survey, researchers were able to determine 4 sample sites for potential sample sites, and they were chosen based on safety, sampleability, deliverability, and science value. So a site with a safe surrounding were selected because the spacecraft must be protected as it descends to, touches, and collects a sample from the asteroid's surface. And the 4 sites were also evaluated based on the amount and the size of sampleable material at that site. Now, the next criteria was deliverability, which evaluates the relative ease for the spacecraft to maneuver in and out of that site. And the 4 sites also have a high science value, meaning that they're rich in things to study, like being able to measure the presence of carbon-rich materials, the presence of hydrated materials, and the diversity in material composition and evidence of primitive materials. Now, in December of 2019, the OSIRIS-REx team chose sites Nightingale as the mission's primary sample site and Osprey as the backup site. And so here is a closer look at the Nightingale site in which OSIRIS-REx touched down and took the sample from. Now, these images were captured and stitched together from October 20th, and that was during the mission's Touch and Go or TAG sample collection event. And this shows the view of the SAM-CAM imager as the spacecraft is approaching and touching down on asteroid Bennu's surface. And this is all happening 320 million kilometers away from Earth. So the sampling event brought the spacecraft all the way down to the Nightingale site, and preliminary data showed us that the sampling head touched the surface for about 6 seconds, and then after which the spacecraft did a control back away burn. Now, in terms of choosing landing sites, like I said, they needed to choose one that was safe, so free of hazards like rocks and boulders. And so the site they chose has a big boulder at its edge, and it's around the size of a humpback whale. So NASA has lovingly called it Mount Doom, just like in Lord of the Rings. And on the right here, you can see that picture. And this image here was created from a set of stereoscopic images, which means that they took many photographs from different angles, kind of like what your eyes do from your 2 eyeballs, taking pictures from different angles or viewing from different angles. And interestingly enough, this image was processed by Brian May and Claudia Manzoni. And if you take a look on the left here, you can see that when the foot touches down, it's actually compressing some of the material on the rocky surface.
Sorry, Rachel, I was going to jump in. Do you mean Brian May of Queen?
I do. Here we go. So yeah, one and the same, Brian May, who daylights as an astrophysicist and is also the lead guitarist of the rock band Queen. But I must warn you that not all astrophysicists are this cool. Now, like I said, Bennu is millions of kilometers away from Earth. And so that means that it takes time for us to send instructions to OSIRIS-REx and for it to receive the instructions and then send data back. So that means that we can't command the spacecraft directly from Earth during the sample collection. And that's why on Tuesday, we saw a real-time animation rather than live feed coming from the spacecraft itself. And so it takes about 18 minutes for signals to travel one way between the team and the spacecraft. And so the team sent preloaded commands so that it could perform the entire tag sequence autonomously. And so that means that the spacecraft was able to make its own guidance calculations based on landmarks that it sees on the surface and also make decisions as to what to do. Now, they do get a little bit of data, but only at a very low data rate. And so they call these bits of data that they do receive, they call them breadcrumbs. And so these bits of data provide them with key pieces of information to let the team know when critical events have been completed in the tag sequence. And so you can imagine how excited the team on Earth was when they received confirmation at 3 p.m. that successful session has occurred. And I just figured I had to show this because I love the excitement that they have from the announcement.
And of course, like this is a 2020 landing. The control room looks a little bit different than they have in the past. They're all wearing masks. I love a little bit later on, you saw Dante Loretta, who's sort of at the back, and he kind of gives like the head rub. But then you see this someone giving sort of like an air hug to each other, which I really appreciate. Yeah. It's sort of like the very 2020 air hug. Because nobody's high-fiving each other. They're all like, pointing to each other. I find it really cute.
But you can tell that they all do want to hug and embrace each other, but they can't. So they're showing some restraint there. But yeah, the excitement is definitely palpable here.
Absolutely.
So let's talk about how do they collect the sample. And so the spacecraft sampling arm, which is the touch and go sample acquisition mechanism, or TAGSAM, and that's shown here. And you can see the round head at the end of the TAGSAM, which is the only part of OSIRIS-REx that actually touches the surface and collects a sample. Now, during the tag maneuver, they extend the sampler head towards Bennu, and the momentum of the spacecraft pushes it against the asteroid surface for about 6 seconds, and that's long enough to obtain a sample. And like I said before, the majority of the collection was over the course of the first 3 seconds of contact. And so when it touches the surface, you can see from this little animation here that it releases a burst of nitrogen gas, and that burst is able to disturb the surface and stir up some of that material for it to be collected by the TAGSAM instrument. And the spacecraft has enough nitrogen to allow for 3 sampling attempts to collect between 60 and 2,000 grams of surface material or of regolith. Now, it takes several days to verify exactly how much material was collected. And one way is to use the spacecraft SAMCAM to do a visual inspection of TAGSAM to see whether or not there are grains of dust in the collector. But they also developed another way to measure the sample mass. So once OSIRIS-REx has backed away from Bennu, we can estimate the amount of sample by spinning the spacecraft with the arm extended, and they compare the spin from when it does have the sample to when it doesn't, and they compare the moment of inertia, and from that change they can tell or give an estimate of how much sample that they have. Now, this is important because if the team decides that they don't have enough, or for some reason the collection was insufficient, they would need to make another collection attempt, and that's why they have 3 bursts of nitrogen gas and not just 1. But it's important to note that they won't sample the same site because they've already disturbed the surface. So they would go to the backup site, Osprey, which is a small crater, and sample from there instead. Now, I think it's important to mention why they chose Bennu, given that we have many, many asteroids in our solar system. So first, they evaluated based on proximity to Earth. Because for sample return, the asteroid needs to be accessible to the spacecraft. And at the time of the mission in 2008, there were over 7,000 near-Earth objects, but only 192 of these met the requirements for proximity. And now the next criteria is the size requirement. So if you have an asteroid with a small diameter, they rotate much more rapidly than those with large diameters. And that's by the conservation of angular momentum. And you can see that similar effect over here with this professor playing with a Hoberman sphere. And you can see the larger sphere turns a lot more slowly than when he pulls the cord and it shrinks down and it rotates a lot more or a lot quicker. Now, if these asteroids are spinning too rapidly, they can actually eject surface material or eject that regolith. And so they wanted an asteroid in that sweet spot. And that size requirement ended up reducing the samples from 192 down to 26 candidate asteroids. Now, the last criteria that they had was composition. So the asteroids are divided into different types based on their chemical composition. And the most primitive ones are carbon rich and haven't changed significantly since they formed over 4 billion years ago. And these asteroids contain organic molecules, volatiles, and amino acids that may have been the precursors to life on Earth. And so of the 26 asteroids on that list, only 12 had a known composition and only 5 were primitive and carbon rich. Now, from these 5, they ended up choosing Bennu, and that's because it has a potentially hazardous orbit for the late 22nd century. Okay, so what can we learn from sampling the asteroid? Well, because Bennu is a leftover fragment from the formation of the solar system, some of the mineral fragments inside Bennu could be older than the solar system itself. So in some ways, it kind of acts as a time capsule from the early solar system, and it was preserved by the vacuum of space. Now, by analyzing a sample from Bennu, it'll help planetary scientists understand the role asteroids may have played in delivering life-forming compounds to Earth. Now, we know from Earth and space-based observations that Bennu is carbon-rich, and that's great because we're carbon-based life forms. So likely, Bennu is rich in organic molecules, which are made of chains of carbon bonded with atoms of oxygen, hydrogen, and other chemicals that are known to be part of living things. Now, besides carbon, Bennu also might have another component that's important to life, and of course, that is water, and that could be trapped in the minerals that make up the asteroid. Now, asteroids are also rich in natural resources, things like iron and aluminum, and precious metals like platinum. And for this reason, companies are working on ways to extract these materials through asteroid mining. And that's important because if they are able to extract materials from asteroids and extract enough hydrogen and oxygen from water locked up in these asteroid minerals, then they could potentially make rocket fuel. And that means that asteroids could serve as fuel stations for deeper space travel. Now, as we saw before, one of the motivations for choosing Bennu was that it is one of the most potentially hazardous asteroids, given that it has a relatively high probability of impacting Earth in the late 22nd century. And NASA puts that probability at 1 in 2,700. So to prepare for this, we want to determine its orbital trajectory, which is affected by the Yarkovsky effect. And so what that is when sunlight strikes a rotating asteroid like Bennu, like you see on the right here, the day side, or the side exposed to light, heats up. And then as the asteroid rotates or turns around, the night side ends up cooling and releasing that heat. And that release of heat actually creates a small amount of thrust. And so the force exerted when sunlight is absorbed by the asteroid and then released as it rotates actually changes the asteroid's trajectory over time. And so that makes it really important for us to analyze this effect and see how it's going to alter the trajectory of asteroid Bennu. And that's it. And I'll stop sharing my screen, and hopefully there are some questions waiting on this. It's so cool. I spent the whole day just going through press conferences and seeing people get excited about the sample, because this has been going on for people who have been on the project since the start for over a decade. That's a long time to wait.
Yeah. And certainly it seems weird now to wait until this moment in 2020. There was probably lots of team members, including some of the Canadian team members, that were probably hoping to be there, at Goddard when it arrived. Mm-hmm. Unfortunately, the borders are closed, couldn't happen, but still very exciting. And I did watch a lot of those news conferences, and there was a lot of really great questions that came out of them, ones that I hadn't really thought of. But if you have questions that you'd like answered, throw them into our chat, and we'll hang around until we've answered them, or just put them into the comments, and we'll answer them later. But first, Rachel, one thing that did come up was, some of like the really big issues that went into the design of the mission, and probably some of the big concerns, like what the things that could have really gone wrong. And the one thing that I heard from the press conferences yesterday was really about the kickback from a lot of that material. So they certainly picked a site that didn't have any of those big boulders, because if those got kicked up, they could certainly damage the spacecraft. And we do see, like in that video, like, wow, like a whole bunch of that it's almost like gravel.
Yeah.
It's not even like a solid rock. It's just like they've often described it as a rubble pile.
Yeah, so they actually describe the asteroid as being quite fluffy because it is a rubble pile. So it's a lot of smaller rocks and chunks of rocks kind of smushed together. And that's what makes this asteroid. And that's why they say it's kind of fluffy.
I wonder if they have to like reclassify it, because sometimes people think of asteroids as this big rock, and I'm sure there are lots of asteroids that are like a big solid floating rock out there, but Bennu certainly seems like it's almost like in a different category.
It does, and it kind of goes to show how much or how little we know about the asteroids in our solar system, because we have the 500,000 known, from which we distilled down to Asteroid Bennu as our candidate, but we are only looking at one in these hundreds of thousands of asteroids going around in the solar system.
Yeah. The other thing that I thought was really funny, I don't know if you heard this, Rachel, and I kind of laughed at the question, like, oh, that's kind of silly. But then like when you hear like the scientists, they like, no, we've thought of pretty much everything. And the question was, seeing all that material being kicked up, and knowing that Asteroid Bennu is very close to the Earth, will this potentially, some of those fragments interact with the Earth, creating a new meteor shower? And I thought, oh, that's kind of like interesting, kind of maybe kind of silly. But then they're like, no, actually, there's actually a real possibility that Bennu now will have created a new meteor shower. And so they thought theoretically, potentially next year, September, but only for the Southern Hemisphere. So I thought that was really funny.
So it's time to book a ticket down to the Southern Hemisphere for for next year.
Absolutely. Well, I've got a couple nieces down there. I think it's time for me to take a trip. We've been cooped up up here for too long. So we've got a couple questions coming in. Clive asked, might any other missions to visit or sample asteroids be planned in the near future? Great question, Clive.
Yeah, so Japan currently has an effort that is actually going to deliver a sample, I think, on December 6th of this year, which is fantastic timing, because they had the Hayabusa 1, which was a spacecraft that visited another asteroid Ryugu, I believe. And now it's on its way to, it's going to Ryugu now. Yeah. And then it went to Itokawa before.
Itokawa, yeah.
Yeah. And so it's going to deliver a sample. So hopefully we can actually compare the sample from the Japanese effort to NASA's sample and see if there's any differences or what's going on here in the 2 out of 500,000 asteroids.
Yeah, what great coincidence that these two missions, are sort of very close together. And even though it's going to take Bennu a few years, there's 2023 is when it's slated to come back, right?
Yeah, so the sample is going to be dropped off by OSIRIS-REx in a sample return capsule, and it's going to be dropped off in a desert somewhere in Utah.
Oh my goodness, I can just like imagine people out in Utah just sort of like hoping maybe that it's going to land in their backyard or something.
Well, that would be pretty amazing if it did.
Yeah, well, and quite similarly, so the Japanese Space Agency, which I am hoping to actually connect with, and maybe we can have a chat here on one of our Ask Us Astronomers about the Hayabusa mission, that's actually going to be landing in the outback in Australia. So very similarly, as you can imagine, if you think about, when astronauts are coming back, sometimes they land in the Siberian desert, sometimes, as we saw with SpaceX, they land in the ocean. I can imagine that landing these samples in the ocean probably wouldn't be a good idea. Just because they're a lot smaller and the possibility of contamination may be greater, right?
Exactly. Yeah. So I'm imagining that when you drop off this capsule into the desert, it's a lot easier to prevent things from getting in than it is from preventing water getting in to this capsule.
I can imagine just like a big shark or a whale, just like coming along, like swallowing it. Now they have this whole other problem
Yeah.
of trying to find the samples.
A shark costing NASA multi-billions of dollars. That would be
Another question coming from Pride. I wonder if as they get denser, they would become more globular and less irregular. So I guess she's talking about the actual asteroids themselves.
Sure. Yeah. So the funny thing about asteroids is that we think of them as the building blocks of planets, or we call them planetesimals. And what's interesting is that when you talk about a planet, we have three criteria that a planet needs to fulfill. And this is one of the reasons why Pluto is not considered a planet anymore. And the three criteria are that it has to orbit around a star, so that for us, it's the sun. It has to have cleared the neighborhood of its orbit, meaning that when it goes around the sun, it's not constantly bumping into things. And the last one is that it has hydrostatic equilibrium, which basically means that it has enough stuff that little bumps and irregularities are actually pulled in by the gravity of that object or of that potential planet. And so with asteroids, because they are doing a smaller version of this, they're not big enough to have that hydrostatic equilibrium and form a nicer sphere. So they all look kind of like chunky potatoes in space.
Yeah, it does sort of like remind me sort of it looks like a top. Like it has like it's really sort of like fat in the middle and skinny sort of like in the bottom and the top.
Yeah, and that's a really good point because it's rotating. And one of the things that happens when spheres rotate, and our Earth does this too, is that it has an equatorial bulge. So at the equator in the midline, it'll bulge out a little bit, and that's because it's spinning fast enough to have that happen. And we call the resulting shape an oblate spheroid, if you ever are curious as to what it's called. But it's kind of the same effect as when Italians spin up their pizza dough and it flattens out.
So I think in honor of Brian May, I think we should start up our own band and call it Oblate Spheroid. I think that should be the name of our band.
I don't know if you'd be very popular.
Another really cool thing about the shape of Bennu is we got our summer intern, Justin, who's been doing a lot of our cool graphics. He made a really cool graphic that you can check out on our social media of just how big Bennu is. So the width of it is about the size of Lionsgate Bridge for people here in Vancouver. And then there is a large boulder sort of like in the Northern Hemisphere. And when I was looking at it and I heard lots of other people sort of like comparing it, the size of it. And so I asked Justin, I was like, does this compare to the size of our dome here at the planetarium? And sure enough, yeah, 30 meters is about the size of that boulder and the same size as our building here at the Space Center. I thought that was pretty neat.
That is pretty cool. And like thinking about how big that asteroid is and landing a small spacecraft on it might seem like an easy task, but I really want to emphasize that this is all happening 320 million kilometers away from Earth. And not only that, because it's so far away, like I mentioned, that there's that 18-minute travel time. So they can't even talk to the spacecraft while it's doing this. So it's very nerve-wracking for all this to be happening so far away.
Right. Amazing. Well, Rachel, this has been a fun week. All get in onto OSIRIS-REx. But we are going to be back here next Thursday for our regular scheduled Ask an Astronomer. And we'll be delving into the space news. And of course, there already is a potential big story coming out that's going to be released next week about the moon, about the Sophia telescope. That's all they've told us so far. We're waiting in anticipation. So we'll probably be talking about those results and, of course, anything else that happens up in space until then. As for OSIRIS-REx, you can look into the event description of the video here for more resources if you want to learn more about OSIRIS-REx. If you want to learn more about what we're doing here at the Space Center, we actually have an event on Halloween, October 31st. You can come and you can learn all about robots. We're going to be talking a lot more about robots as we get closer, of course, to talking about Mars, the planet of robots, in February, but you can come and we're going to have an experience here in the building with some of our staff. It's going to be really fun. That's on October 31st. And then as we roll into our other months, we're going to be doing lots of other special events. But you know what? We're going to be here every second week on YouTube. So glad you could join us. Hope to see you again next time.
Bye.